Hi, in this tutorial I'm just going to go over covalent bonding. I'm just going to bring up hydrogen atom just so we can explain a little bit about shells and orbitals again. So in this tutorial, because we're talking about covalent bonding, if you've seen the ionic bonding tutorials, you'll realise that what happens in ionic bonding is that electrons move across onto other atoms and they become positively charged if it's hydrogen, and say if it's chlorine, that'll pick up an electron and become negatively charged because the balance of protons to electrons changes. So for hydrogen, if it loses an electron, it has a positive charge left behind, so it becomes positive. And similarly for chlorine, you'd have an extra electron which would make it negatively charged. For covalent bonding, it's not quite the same. What happens is, if I bring carbon up here, so carbon's in group 4, which means it's got 4 electrons that are ready to pair up. Remember, we've got the octet rule where we want to have 8 electrons in the outer shells, apart from the first shell which has 2. So with covalent bonding, what happens is the 2 atoms share bonding. So if I quickly draw a sketch of hydrogen here, I'll draw the hydrogen atom here and put the nucleus in the middle. I'm just going to draw the outer shell of carbon. Draw the outer shell of carbon there. There's carbon, carbon and hydrogen. I'll just choose a different colour for the electrons here. Put an electron there for hydrogen, and on carbon it's got 4 on the outside there like that. In fact, what I'll do, I'll just change them to a different colour as well, just to indicate that these electrons here are actually belonging to carbon. Okay, so that's carbon's outer shell. I've missed the inner shell ones out because they're not going to take part. It's on the outer shell, or the valence shell. So it's the valence shell. Or valence electrons. They're going to take part in the bonding. Okay, so it's the outer 4. Now if we form a bond between these, what a bond means is that, in this case a covalent bond, means that this carbon atom is going to share the electron of the hydrogen atom with hydrogen. So the hydrogen will think it's got 2 and the carbon will think it's got an extra one here. And this is why carbon can form 4 bonds, because it can share 4 times 4 of its electrons with other atoms. Now in the case of hydrogen, it can only share with one more atom because it's only got 1 electron to fill up. So in the 1s orbital here, this first shell, it only needs an extra electron, so it only needs to form 1 more bond. So if we draw, I'll just move this out of the way a second, if we draw methane, which is one of the simplest hydrocarbons, I'm just going to draw it a little bit like this. This will be hydrogen. I'll put hydrogen here. And if I draw another hydrogen here, I'll draw another one there. So this is the outer shell. I'll draw another one there. And what I'm going to do, I'm going to colour in the electrons for hydrogen like this. And as you can see now, it looks like carbon has got, so carbon, if I just move this carbon here, that's carbon, and then I'll just change it to green to match its electrons. So we now look at carbon here, it now looks like it's got an octet. It's got 8 electrons in this outer shell here, which is great because that means it's happy and it's stable. Now if we look at hydrogen, hydrogen now looks like it's got 2 electrons, and again that's great because that's exactly what it wanted to do. But really it's being deceived because its electron is helping this one feel better, and the carbon's electrons are making hydrogen feel better. And that's called a covalent bond, where they share electrons. Now, one more thing happens with covalent bonds. Unless the atoms that are sharing bonds, if I draw the simplest molecule in the world, I suppose, in the universe, is hydrogen. And we draw it as a Lewis structure like this, where we've got the single bond is represented like that. Now, if I draw two electrons here that are sharing, two electrons form a bond, a single bond. And if I draw the orbital round, hopefully you can see. It's not meant to be a different size, but in fact it's very important that it's not a different size. So what I'll do is I'll get a circle like this. I'm just going to draw a circle. Okay, I'll copy that now, just to make sure I get the sizes. I'll drag that down there like that. Okay. Now the reason I was interested in it being the right size as well is because it really represents the electron density, or where the electrons are. So if you think of it as the planets going around the sun, and that structure, if we had the simple structure, the Rutherford model for the atoms, then the electrons can't tell which hydrogen they're at, or they don't prefer to be at any hydrogen, basically, because they're both the same kind of atom, so they've got the same attraction towards the electrons. Now, if you go to a different element, for example carbon, so we change this now, I'll just copy it and paste it very quickly. If we change this over here, and change this hydrogen, rid of that, we change this to carbon, I'll draw it in green again. Okay, now carbon needs to have 8, but I'm just looking at this bond here. Now we will find that the carbon atom here, just drag this out, will be a lot bigger. But not only is it bigger, not only is that carbon bigger, it's also got more protons. It's got 6 protons as opposed to 1 proton. So imagine that it's got 6 times the positive charge. Now what that does is it drags the electrons towards itself more. It's called electronegative, and it's a bit hungry for those electrons. So this is more electronegative. So carbon is more electronegative. Okay, now I'll put all these things up on the website just so you can see what I mean by this. Now what that means, being more electronegative, is that it attracts the electrons towards itself. So imagine the electrons are moving in this direction and spend more time on carbon than hydrogen. So hydrogen is again a bit of a raw deal really when it comes to sharing of the electrons. Now that is called a polar bond. I have to excuse my, forgive my accent there. It's polar, as in polar bear. And that doesn't help either because I can't say bear properly. So polar bond means it's got some direction to it. It's not equal on both sides. It's got some direction, so the electrons like to move towards carbon, which is a bit more electronegative. So it draws the electrons towards itself. And that's all that really means. That's a polar bond. Now the extreme of a polar bond would be an ionic bond, because really the electrons are dragged that far over that they actually sit on the atom. So if you remember the tutorial on ionic bonding, where the sodium chloride, for example, which has a nice crystalline structure made up of sodium atoms, sodium ions, should I say. Ion is an atom that's either gained charge or lost some charge. So that's made up of ionic species, which is basically the loss of the extreme of the polar bond. It's all gone over to one atom. But in a polar covalent bond, there is still some electrons going and whizzing around the other bonds like this. So rather than just whizzing around carbon, it does spend some time on hydrogen, but not much. It spends most of its time because it's bigger. So that is a polar bond. I'm just going to clean this up, and this is how the share. You can see how it thinks. So just to recap, really, the hydrogen thinks it's got 2, but it's actually, because it's sharing with carbon, and carbon thinks it's got 8, but actually it's sharing with hydrogen. So it's a bit of a mismatch of things there. Okay, so that's a covalent bond. I'm just going to end a little bit with some covalent structures, because covalent bonds are great, and it's what me and you are made out of. Okay, a majority of the bonds in our body are covalent bonds. We have a few ionic bonds, and we've got ions floating around our blood and things like that, but a lot of bonds are covalent bonds. Now, I drew this structure earlier. I'll try and make it a little bit bigger. Okay, so this structure here, imagine each one of those balls is carbon. So carbon's made up of that. So carbon can form 4 bonds because it's got 4 electrons that need to be paired up. And if you look, if this central one here, it's got 4 bonds coming off it. And this structure here, which looks like a bit like a triangular based pyramid with another point sticking on the top, like an antenna, is called a tetrahedral structure. I'll just write that for you. So it's tetrahedral. And you'll come across that word quite a lot in chemistry, because a lot of organic compounds have this tetrahedral shape. And it just means there's 1, 2, 3, 4, 5 carbons, with the central one having 4 bonds to each of the ones on the outside, and it has a tetrahedral shape to it. Put all the points together, and that's tetrahedral. So this is a quite useful word that you should try and remember if you want. So useful words, when I'm writing my notes, I usually put a cloud around so I can see it straight away. Okay, so this structure is diamond. So diamond's one of the allotropes of carbon. Allotrope just means it's like a natural form of carbon. So carbon can exist as the element in several forms, and one of them's diamond. So diamond, we've all heard of diamond. Probably parents have probably got one on the rings or things like that. So diamonds is a very hard substance. So these form very complex, large structures, these covalent bonds, and they're extremely hard for diamond. Another structure, which you'll have to forgive me, the structure is not perfect, but it's just based a little bit on, let's move it a little bit. So it's still got that tetrahedral structure, but this should be have a slight angle to it. It's not as straight as that in real life. I drew it quickly based on this structure, but you see it's still got a tetrahedral structure. And imagine the blue there. Let me draw a line to that. So the blue, this one here, is the element silicon, and this one here is the element oxygen. Then that structure there is a massive is a massive structure, and it just goes on and on and on, just like structure of diamond goes on. And that's called silicon dioxide, and we write silicon dioxide like that. But what we're trying to say is that that is the small part. That's a small building block. If you look at silicon dioxide, it's all made up of that, but it actually connects. It doesn't just end. It's not just silica and oxygen together and then another silica and oxygen. They're all bonded together like this in a massive structure. And that's basically the structure of sand. Silicon dioxide is sand, or quartz, or silica. They're all different forms of silicon dioxide. So that's a basic introduction to covalent bonding. So it's an extreme of ionic bonding, so the electrons aren't fully captured, they're shared. But you can have non-polar bonding, and these would usually be what we call homoatomic, diatomic molecules like hydrogen. So it's got the same element on both sides, so there's no way of differentiating or choosing one over the other. And we've got polar bonds, which are more common, I suppose. Polar bonds, which are things like CH, OH, and things like that. So that's it for introduction to covalent bonding. I'll put up some more structures and some of these words I'll type out so you can read them in my handwriting. So until next time, see you soon.